So whether we're talking about organic chemistry or any other chemical branch, one of the primary rationales of studying chemical science is to determine why reactions happen. So chemistry is the central science. We like to be able to predict when we mix two chemicals together what the outcome is going to be. And there are physical driving forces which cause these reactions to occur, and they can be very nicely grouped into one of two types. A chemical reaction should decrease the energy of the system, which means the energy of the product should be lower in energy than the reactants. Of course, the proper chemical term for this is the enthalpy. So in chemical reactions that release energy or lower the energy state, we call these reactions exothermic. And there are lots of ways for us to classify an exothermic reaction. One way is to use the mathematical definition that the delta H is less than 0. What this means is that the energy of the products is lower than the energy of the reactants. To say it another way, the bonds that are formed are lower in energy than the bonds that are broken. So in other words, we have stronger bonds that are made relative to the bonds that have been broken. Now graphically we can represent an exothermic reaction in this manner. If this is our enthalpy on the y-axis and reaction coordinate, on the x-axis, the energy of our reactants, the energy of our products. This, of course, is going to be our energy of activation. Well, this will be our delta H. And since delta is always final minus initial, this will be less than 0. So this is characteristic of an exothermic reaction. Now, if an exothermic reaction is a positive driving force, then a reaction in which the energy is absorbed should be a negative driving force. So let's talk about endothermic reactions. So in an endothermic reaction, that looks really bad. Let me fix that. The delta H will be greater than 0. Energy is absorbed. This means that the temperature of the surroundings, and it's important to remember that the solvent is part of the chemical surroundings. The temperature of the surroundings will decrease. Therefore, the solution loses heat energy and gets colder. So a cold pack is a prototypical endothermic reaction. This means that the bonds we make are weaker than the bonds that we break. If we were to examine a potential energy diagram where once again we have enthalpy as a function of reaction coordinate. Of course, the difference between the transition state, of course this transition state is where bonds are beginning to break and bonds are beginning to make. Sometimes this happens in one step and it's called concerted. Other times it happens in discrete steps and it's called stepwise. And we'll see examples of both types of mechanisms throughout this course. This is the energy of activation. And of course, here is our delta H. Again, delta H is final minus initial, so this delta H will always be greater than 0. So the first driving force is low energy, which means exothermic. Is typically preferred. Let's talk about driving force number 2. Driving force number 1, low enthalpy or energy. Driving force number 2, increasing disorder or entropy. Entropy is full of pitfalls, but essentially the more statistical, probable locations that these molecules can occupy in three-dimensional space, the greater the entropy is going to be. So, for example, we say that as we go from a solid to a liquid to a gas, the delta S is greater than 0. What we're doing is breaking intermolecular forces as we go from solids to liquids and as we go from liquids to gases. In the context of a chemical reaction, we'll simply count the number of moles of gas in reactants. We'll compare it to moles of gas in products. And if moles of gas of products has more, then we have a positive delta S. Whereas if moles of gas of reactants have more, then we have a negative delta S. Now, it is a little trickier than this. So anytime we increase the temperature, we are emphasizing the entropic contribution to free energy, and we are de-emphasizing the enthalpic contribution to free energy. For example, let me just use a reaction that we're going to learn about later in the course, where we brominate a double bond. You're going from 2 molecules to 1 molecule. Everything is in the liquid state. So if I were to increase the temperature, I would favor the reverse reaction, the decomposition of this alkyl halide. Increasing the temperature is going to emphasize where delta S is going to be predominant. Entropy increases as I go from products to reactants. Energy decreases as I go from reactants to products. So if I lowered the temperature, it would favor the forward reaction, whereas if I raised the temperature, it would favor the reverse reaction. These really are all principles that you should have mastered in general chemistry too, but I often find that students struggle with them, and so you cannot compartmentalize that which you learned in Gen Chem 1 and 2 and live under the delusion that you will not be applying these in organic chemistry. You will not be able to steer away from thermodynamics, kinetics, equilibrium, or acid-base chemistry throughout Organic 1 and Organic 2. And so, word to the wise, it's really good to have this mastered before you attempt to move any further with advanced material that I present in the course. So these are our two great driving forces, and cumulatively taken together, they can help us predict whether a reaction will be spontaneous or not. So I think we're all familiar with Gibbs free energy equation. And from Gibbs free energy equation, we can actually make what is known as a sign chart. Delta H can be positive or negative. Delta S can be positive or negative. And so you come up with 4 different permutations of delta H, delta S combinations. Delta G can be negative at very high temperatures if both delta H and delta S are positive. At very low temperatures if delta H and delta S are negative. It can never be negative if delta H is positive and delta S is negative, because a negative minus a minus will only make that value, that numerical value, more positive. And of course, it will always be spontaneous when delta H is negative or delta S is positive. Let's take a closer look at this. In the top condition, one driving force is present. Number 2, 0 driving forces are present. 3, both driving forces are present. And number 4, 1 driving force is present. So when we take this data holistically, at least one of those 2 driving forces must be present in order for the reaction to be spontaneous. Finally, let's look at this term delta H. When heat is released into the surroundings, what this really does is increase the delta S of the surroundings. In other words, Gibbs free energy equation is ultimately found in the entropic state function. Delta G equals delta S of the surroundings plus delta S of the system. Just so happens that we measure delta S by the change in temperature over the absolute temperature. So this is an algebraic approximation. Once I plug this in for delta S surrounding, we are going to yield the familiar delta H minus T delta S. The delta S of the universe must always increase for a spontaneous process to occur. And it's delta S of the surroundings plus the delta S of the system. If the delta S of the universe is positive, delta G will be negative. So I haven't written this in a mathematical proper way. I'm simply emphasizing that that delta G is an algebraic sum of the delta S of the surroundings and the delta S of the system. If the delta S of the surroundings is negative, that means we had an endothermic process. As long as the delta S of the system is more positive than the delta S of the surroundings is negative, we'll still have a spontaneous process. Finally, I want to look at the Morse potential to show you a very fundamental relationship between bond making and bond breaking. So we're going to look at potential energy as a function of internuclear distance. This relationship is known by one of two names, either a Morse potential or in the theoretical world, this is called a Lennard-Jones potential. And the relationship looks like this. If you have two atoms, A and B, that are infinitely far apart. If you have two atoms, B and A, that are infinitely close together, the potential energy is greater than it is at the optimized distance of A and B, where A and B form the most stable covalent bond. So this distance is the covalent bond length. When two atoms approach one another to make a bond, they lower the potential energy. When two atoms move apart to optimize a covalent bond, they lower the potential energy. So here's the take-home message. Bond making is exothermic. Always, 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 say it with me, always. Bond making is exothermic. If I break this bond, if I move them infinitely far apart or infinitely close together, the energy increases in this system. Point number two, bond breaking is endothermic. In lecture, I need you to be absolutely clear that bond making releases energy, bond breaking requires energy, and now we can go back and make sense of our graphs. Because whether we were looking at an endothermic process or an exothermic process, here's our endothermic process, here's our exothermic process, the activation of energy barrier is positive. This means to kickstart a reaction, bonds are broken. The first step in either this endothermic reaction or this exothermic reaction, and remember that this is potential energy as a function of the reaction coordinate, time if you will. Potential energy as a function of reaction coordinate, time if you will. The energy of activation is going to be positive because the first part of each of those processes is an endothermic process. And the second part of each of these processes is exothermic. In an overall exothermic, the exothermic process releases more energy than the endothermic process required, and vice versa with an endothermic reaction. Endothermic, exothermic. Temperature will increase because we're measuring the surroundings. Temperature will decrease because we're measuring the surroundings. The driving force in making bonds is to lower the energy of the system such that I release energy to increase the entropy of the surroundings. The reason we make bonds is to ultimately increase the delta S of the surroundings. We do this by decreasing the delta H of the system. So in the next screencast, I'm going to talk at length about valence bond theory, about hybridization, and about how we use a novel method called ODEC to rationalize structures, geometries, formal charges, and rudimentary mechanisms. It is all rooted in this central idea. We want to release energy to increase the delta S of the surroundings.